Deep in the vast expanse of the universe, where stars are born and galaxies collide, lies a cosmic spectacle so strange and mesmerizing that it defies imagination. Picture this: two galaxies locked in a slow-motion dance of destruction and creation, stretching across millions of light years with tendrils of stars and gas swirling like cosmic ribbons. This is the Antennae Galaxies, a pair of colliding galaxies that hold secrets so profound they challenge everything we think we know about the universe. But what makes these galaxies so extraordinary? What strange phenomena unfold in this chaotic corner of space? Today, we're diving into 25 of the most bizarre and fascinating mysteries of the Antennae Galaxies phenomena that will leave you questioning the very fabric of reality. From hypervelocity stars racing through the void to supermassive black holes devouring everything in their path, each discovery is more mind-bending than the last. So buckle up, because by the end of this journey, you'll see the universe in a whole new light, ready to explore the cosmic enigma of the Antennae Galaxies. Let's begin. Now, let's zoom in on the very heart of this cosmic drama, the collision itself. The Antennae Galaxies are not just one galaxy, but two, caught in a gravitational tango that has been unfolding for hundreds of millions of years. Imagine two massive spirals, each home to billions of stars, slowly being pulled together by the invisible force of gravity. As they approach, their delicate structures begin to warp and stretch, like two dancers spinning closer and closer until their arms intertwine. This collision is not a sudden crash, but a gradual, breathtaking merger that reshapes everything in its path. The result, a chaotic yet beautiful spectacle of swirling gas, dust, and stars, all set against the backdrop of deep space. But this isn't just a visual marvel, it's a cosmic engine of creation. The immense gravitational forces at play compress clouds of gas, igniting the birth of countless new stars. In fact, the Antennae Galaxies are one of the most active star-forming regions in the nearby universe, a testament to the transformative power of galactic collisions. So, as we witness these two galaxies merging, we're not just watching destruction, we're seeing the universe's way of building something entirely new. And this is only the beginning of the strange phenomena that make the Antennae Galaxies so extraordinary. Now, let's turn our attention to one of the most striking features of the Antennae Galaxies, the tidal tails. These enormous, sweeping arcs of stars, gas, and dust stretch far beyond the main bodies of the galaxies, like cosmic ribbons trailing through the void. But what exactly are these tidal tails, and how do they form? As the two galaxies collide, their immense gravitational forces pull and twist at each other, creating these dramatic extensions. Think of it like two whirlpools spinning close together. Their edges stretch and distort as they interact, sending streams of material spiraling outward. These tidal tails are not just random debris, they're a direct result of the galaxy's gravitational dance, a visible record of the forces reshaping them. Over time, these tails will play a crucial role in the galaxy's evolution. Some of the material may fall back into the galaxies, fueling new star formation, while other parts may drift away, seeding the surrounding space with the building blocks of future stars and planets. The tidal tails are more than just a beautiful byproduct of the collision, they're a key part of the story, showing us how the Antennae Galaxies are transforming and leaving their mark on the cosmos. And as we continue to explore these galaxies, we'll see even more ways this cosmic collision is shaping their destiny. Now, shifting our gaze to another breathtaking result of this galactic collision, we encounter the phenomenon of superstar clusters. These are not your average star clusters, they are incredibly dense, packed with hundreds of thousands of young stars, all born from the chaos of the Antennae Galaxies collision. Imagine a cosmic fireworks display where the collision acts as the spark, igniting the birth of these dazzling stellar groups. But what makes these superstar clusters so special? Unlike smaller, more common star clusters, these giants are formed under extreme conditions where vast clouds of gas and dust are compressed and heated by the immense gravitational forces of the colliding galaxies. This process triggers a burst of star formation on a scale rarely seen elsewhere in the universe. These clusters are like time capsules, offering us a glimpse into the early stages of star formation and galactic evolution. They are also key players in shaping the future of the Antennae Galaxies. As these young stars age, some will explode as supernovae, enriching the surrounding space with heavy elements that will eventually form new stars, planets, and even life. Others may merge, creating even more massive stars or even black holes. The superstar clusters are not just a byproduct of the collision. They are a driving force in the ongoing transformation of the Antennae Galaxies, helping to sculpt their future and leaving a lasting impact on the cosmos. As we continue to explore these galaxies, we'll uncover even more ways these superstar clusters are shaping their destiny. Now, let's turn our attention to one of the most fascinating and mysterious aspects of the Antennae Galaxies, the supermassive black holes lurking at their cores. These cosmic giants, each millions of times more massive than our Sun, are not just sitting quietly. The collision between the two galaxies has stirred them into a frenzy of activity. As the galaxies merge, their central black holes are drawn closer together, creating a gravitational tug-of-war that sends shockwaves through the surrounding space. This interaction causes the black holes to devour vast amounts of gas, dust, and even stars, heating the material to incredible temperatures and causing it to glow brightly across multiple wavelengths. This heightened activity makes the black holes some of the most energetic objects in the Antennae Galaxies, emitting powerful jets of radiation and particles that can stretch for thousands of light years. But the story doesn't end there. Over time, these supermassive black holes are expected to spiral closer and closer, eventually merging into a single, even more massive black hole. This cosmic dance not only shapes the galaxies, but also provides scientists with a rare opportunity to study the behavior of black holes in extreme environments. The Antennae Galaxies are like a cosmic laboratory, offering us a front-row seat to the dramatic and dynamic processes that govern the universe's most enigmatic objects. As we continue to explore, we'll uncover even more about how these black holes influence the galaxy's evolution and what their future holds. Now, shifting our gaze to another remarkable feature of the Antennae Galaxies, let's explore the intense infrared light that radiates from this cosmic collision. Unlike the visible light we see with our eyes, infrared light reveals a hidden layer of activity within these galaxies. The reason for this intense emission lies in the vast clouds of dust scattered throughout the antennae. As the galaxies collide, the shock waves from the merger compress gas and dust, triggering the birth of countless new stars. These young stars, burning fiercely, heat the surrounding dust to extreme temperatures, causing it to glow brightly in infrared wavelength. But it's not just the stars' hidden cosmic processes, such as the activity of supermassive black holes and supernova explosions, also contribute to this infrared glow. The dust acts like a cosmic blanket, absorbing the energy from these events and re-emitting it as infrared light. This makes the Antennae Galaxies one of the brightest infrared sources in the universe, offering astronomers a unique window into the hidden mechanisms driving galactic evolution. By studying this infrared emission, scientists can peer through the dust to uncover the secrets of star formation, black hole activity, and the intricate dance of matter and energy that shapes these galaxies. As we continue our journey, we'll see how this infrared light not only illuminates the Antennae Galaxies, but also deepens our understanding of the universe's most energetic processes. Now, let's turn our attention to one of the most explosive events in the universe: gamma-ray bursts. These rare but incredibly powerful phenomena have been observed in the Antennae Galaxies, adding another layer of intrigue to this cosmic collision. Gamma-ray bursts are brief flashes of intense gamma-ray radiation, often lasting just a few seconds, but they release more energy than our Sun will emit in its entire lifetime. In the Antennae Galaxies, these bursts are thought to be linked to the dramatic deaths of massive stars. When a star many times more massive than our Sun exhausts its fuel, it collapses under its own gravity, triggering a catastrophic explosion known as a supernova. In some cases, this collapse leads to the formation of a black hole, and as matter spirals into the newly formed black hole, it can produce jets of particles traveling at nearly the speed of light. These jets, when pointed toward Earth, are what we detect as gamma-ray bursts. The Antennae Galaxies, with their high rate of star formation and frequent supernova explosions, provide the perfect environment for these bursts to occur. While gamma-ray bursts are fleeting, their impact is profound. They offer scientists a unique opportunity to study the extreme conditions of the universe, from the birth of black holes to the behavior of matter at the edge of physics. As we continue to explore the Antennae Galaxies, these bursts remind us of the incredible forces at play in the cosmos, forces that shape not only galaxies but our understanding of the universe itself. Now, shifting our gaze to another extraordinary phenomenon, let's explore the hypervelocity stars racing through the Antennae Galaxies. These stars are cosmic speedsters, flung out at mind-boggling velocities, some traveling at speeds exceeding 1 million miles per hour. But how do stars reach such incredible speeds? The answer lies in the chaotic gravitational dance of the colliding galaxies. As the Antennae Galaxies merge, their immense gravitational forces interact in unpredictable ways. In some cases, stars orbiting near the supermassive black holes at the galaxy's cores can be slingshotted outward with tremendous force. Imagine a cosmic game of pinball where stars are the balls and the black holes are the flippers, sending them hurtling across space. These hypervelocity stars are not just fascinating for their speed, they also carry clues about the environments they were ejected from. By studying their trajectories and compositions, astronomers can piece together the history of the Antennae Galaxies collision and the extreme conditions within their cores. What's even more intriguing is that some of these stars may eventually escape their galaxies entirely, becoming intergalactic wanderers drifting through the vast emptiness of space. This phenomenon highlights the sheer power of gravitational interactions and the dynamic nature of the Antennae Galaxies, where even the stars themselves are caught in a cosmic whirlwind. As we continue to unravel the mysteries of these hypervelocity stars, we gain deeper insights into the forces that shape not just galaxies, but the very fabric of the universe. Now, let's turn our attention to one of the most striking features of these galaxies, their unmistakable shape. The Antennae Galaxies are named for their dramatic, antenna-like appearance, a result of their ongoing collision. As the two spiral galaxies collide, their gravitational forces pull and stretch their spiral arms into long, sweeping arcs that resemble the antennae of an insect. This process, known as tidal interaction, is a cosmic tug-of-war where gravity reshapes the galaxies into something entirely new. The once orderly spiral arms are now twisted and distorted, creating a chaotic yet beautiful structure that spans hundreds of thousands of light years. What's fascinating is that this unique shape isn't just a visual spectacle, it's a snapshot of galactic evolution in action. The stretched arms are filled with gas, dust, and newly forming stars, making them hotspots of cosmic activity. Over time, these tidal tails will continue to evolve, eventually fading as the galaxies merge into a single entity. The antennae's shape serves as a reminder of the immense forces at play in the universe, where even the grandest structures are not immune to change. As we study this phenomenon, we gain a deeper appreciation for the dynamic and ever-changing nature of galaxies, and how collisions like this one shape the cosmos we see today. Next, we'll explore how dark matter plays a hidden yet crucial role in this galactic drama. Now, let's peel back another layer of this cosmic mystery and explore the invisible force shaping the Antennae Galaxies' dark matter. While we can't see dark matter directly, its presence is felt through its gravitational influence, which plays a critical role in the collision and evolution of these galaxies. As the two galaxies collide, their dark matter halos, vast, invisible clouds surrounding them, interact in ways that are just as dramatic as the visible chaos. These halos act like cosmic scaffolding, guiding the movement of stars, gas, and dust, and influencing how the galaxies merge over time. Without dark matter, the collision would look very different, and the galaxies might not have formed the stunning tidal tails we see today. Scientists believe that dark matter makes up about 85% of the total mass in the Antennae Galaxies, meaning it's the dominant force shaping their destiny. Its distribution affects how quickly the galaxies merge and how new stars form in the process. As the collision continues, dark matter will also determine the final structure of the merged galaxy, likely resulting in a massive elliptical galaxy. Understanding dark matter in the Antennae Galaxies not only helps us decode their future, but also sheds light on the role this mysterious substance plays in the evolution of galaxies across the universe. Next, we'll dive into why the Antennae Galaxies are classified as starburst galaxies and what makes their star formation so extraordinary. Now, shifting our gaze to the heart of the Antennae Galaxies, we uncover one of their most dazzling features: their classification as starburst galaxies. But what exactly does this mean? Starburst galaxies are cosmic powerhouses, regions of the universe where stars are born at an astonishing rate, far exceeding what we see in typical galaxies like our own Milky Way. In the case of the Antennae Galaxies, the ongoing collision has triggered a frenzy of star formation, turning them into one of the most active stellar nurseries in the observable universe. The collision has compressed vast clouds of gas and dust, creating the perfect conditions for new stars to ignite. Imagine a cosmic fireworks display where thousands of stars burst into life in a relatively short period of time. This intense activity is why the Antennae Galaxies are considered starburst galaxies. In fact, they produce new stars at a rate hundreds of times faster than our galaxy. To put it into perspective, while the Milky Way forms about 1 or 2 new stars each year, the Antennae Galaxies are churning out dozens, if not hundreds, in the same time frame. What makes this phenomenon even more fascinating is the sheer scale of the star-forming regions. Massive clusters of young, hot stars light up the galaxies, their brilliance outshining older, cooler stars. These clusters are so dense and luminous that they can be seen from millions of light years away. But this rapid star formation comes at a cost. The energy released by these newborn stars heats up the surrounding gas, creating powerful shockwaves that ripple through the galaxies. These shockwaves can trigger even more star formation, creating a self-sustaining cycle of stellar birth. However, this burst of activity won't last forever. Starburst galaxies like the Antennae eventually exhaust their gas reserves, slowing down star formation over time. But for now, the Antennae Galaxies are a testament to the dynamic and ever-changing nature of the universe. Their starburst phase not only highlights the dramatic effects of galactic collisions, but also provides a glimpse into how galaxies evolve over billions of years. Next, we'll explore the role of molecular clouds in this stellar spectacle and how they serve as the birthplaces of stars and planetary systems. Now, let's dive into the cosmic cradles of the Antennae Galaxies, the dense molecular clouds that play a pivotal role in the birth of stars and planetary systems. These vast, cold clouds of gas and dust are the raw materials of the universe, the very building blocks from which stars and planets emerge. In the Antennae Galaxies, the collision has compressed these molecular clouds, creating regions so dense that gravity takes over, pulling the material together until it ignites into new stars. Imagine these molecular clouds as cosmic nurseries where the seeds of future stars are sown. Within these clouds, pockets of gas and dust collapse under their own weight, forming dense cores. As these cores grow hotter and denser, nuclear fusion begins and a new star is born. But it's not just stars that form here. Planetary systems also take shape from the leftover material swirling around these newborn stars. This process is how our own solar system likely began, billions of years ago. What makes the molecular clouds in the Antennae Galaxies so extraordinary is their sheer scale and activity. The collision has stirred up these clouds, triggering a frenzy of star formation. Some of these clouds are so massive that they give birth to entire clusters of stars at once, creating dazzling stellar neighborhoods that light up the galaxies. These clusters are often home to some of the youngest and most massive stars in the universe, their intense radiation sculpting the surrounding gas into intricate shapes and structures. But molecular clouds are more than just star factories, they're also cosmic recycling centers. When massive stars die in spectacular supernova explosions, they blast their material back into space, enriching the molecular clouds with heavy elements like carbon, oxygen, and iron. These elements become the building blocks for new stars, planets, and even life itself. In this way, the Antennae Galaxies are not just creating stars, they're weaving the fabric of future worlds. As we continue to explore the Antennae Galaxies, the role of molecular clouds reminds us of the intricate and interconnected processes that shape the universe. From the birth of stars to the formation of planets, these clouds are at the heart of cosmic evolution. Next, we'll turn our attention to the numerous X-ray sources detected in the Antennae Galaxies, shedding light on the high-energy phenomena that accompany this galactic collision. Now, shifting our gaze to the high-energy side of the Antennae Galaxies, we uncover a universe of X-ray sources that reveal some of the most extreme and dynamic processes in space. These X-ray emissions are like cosmic fingerprints, pointing us toward black holes, neutron stars, and vast clouds of superheated gas. Each of these sources tells a story of immense energy and the dramatic forces at play during this galactic collision. At the heart of the Antennae Galaxies, supermassive black holes are feasting on the surrounding material, releasing torrents of X-rays as they do so. These black holes, hidden within the cores of the colliding galaxies, are surrounded by swirling disks of gas and dust. As this material spirals inward, it heats up to millions of degrees, emitting X-rays that can be detected across vast distances. These observations give us a glimpse into the intense activity happening at the centers of the galaxies, where gravity reigns supreme. But black holes aren't the only X-ray powerhouses in the Antennae Galaxies. Neutron stars, the dense remnants of massive stars that have exploded as supernova, also contribute to the X-ray glow. These incredibly dense objects, often no larger than a city, can spin at dizzying speeds, emitting beams of X-rays that sweep across space like cosmic lighthouses. Some neutron stars in the Antennae Galaxies are part of binary systems, where they pull material from a companion star, creating bursts of X-rays as the gas crashes onto their surfaces. Then there are the hot gas clouds, vast regions of superheated plasma that fill the space between stars. The collision of the Antennae Galaxies has compressed and heated this gas, causing it to emit X-rays as well. These clouds are not just remnants of the collision, they're active participants in the ongoing drama, shaping the galaxy's structure and influencing the birth of new stars. The X-rays they emit provide a map of the turbulent environment, showing us where the collision's energy is being released. What makes these X-ray sources so fascinating is how they connect the Antennae Galaxies to the broader universe. By studying them, astronomers can learn about the life cycles of stars, the behavior of black holes, and the dynamics of galactic collisions. The X-ray emissions are like a cosmic language, revealing secrets that would otherwise remain hidden in the darkness of space. As we move forward, we'll explore another intriguing aspect of the Antennae Galaxies, the fate of these colliding giants, and what their eventual merger will mean for the future of this cosmic dance. Now let's peer into the future of the Antennae Galaxies and uncover what lies ahead for these cosmic titans. As the collision continues, the galaxies are locked in a gravitational dance that will ultimately reshape their destiny. Over the next few 100 million years, the Antennae Galaxies will complete their merger, transforming into a single, massive elliptical galaxy. This process is not just a cosmic spectacle, it's a fundamental chapter in the story of galactic evolution. The merger will bring about dramatic changes. The chaotic gravitational forces that have already stretched the galaxies into their iconic antennae shape will continue to pull and twist their structures. The tidal tails, those vast streams of stars and gas, will gradually fade as the galaxy's cores draw closer together. The intense star formation triggered by the collision will eventually slow down as the gas and dust needed to fuel new stars are consumed or dispersed. As the galaxies merge, their supermassive black holes will also play a pivotal role. Currently orbiting each other at the centers of their respective galaxies, these black holes will spiral inward, drawn together by gravity. Eventually, they will collide, releasing an immense burst of energy in the form of gravitational waves. This event will mark the final act of the merger, leaving behind a single, even more massive black hole at the heart of the new elliptical galaxy. The resulting galaxy will be strikingly different from the spiral structures we see today. Elliptical galaxies are characterized by their smooth, rounded shapes and lack of spiral arms. They are also home to older stellar populations, as the frenetic star formation of the merger era gives way to a quieter, more stable phase. The Antennae Galaxies, once vibrant with young stars and glowing gas clouds, will settle into a more serene existence, their fiery youth giving way to a calmer maturity. This transformation is not unique to the Antennae Galaxies. It's a process that has shaped countless galaxies throughout the universe. By studying this merger, astronomers gain valuable insights into how galaxies evolve over time. The Antennae Galaxies serve as a cosmic laboratory, offering a glimpse into the forces that drive galactic change and the ultimate fate of colliding systems. As we look ahead, the story of the Antennae Galaxies reminds us that the universe is in a constant state of flux. What we see today is just a snapshot in time, a fleeting moment in the grand cosmic dance. And with that, we turn our attention to another fascinating phenomenon: the role of cosmic recycling in shaping the future of these galaxies. Now, let's dive into one of the most fascinating aspects of the Antennae Galaxies: cosmic recycling. As these two galaxies collide, they're not just tearing each other apart, they're also setting the stage for a remarkable process of renewal. The collision is recycling vast amounts of gas and dust, creating the raw materials needed to fuel new generations of stars and planets. It's like a cosmic recycling plant where the debris from the old becomes the foundation for the new. During the collision, the gravitational forces at play pull and compress the gas and dust within the galaxies. This compression triggers the formation of dense molecular clouds which act as stellar nurseries. Within these clouds, pockets of gas collapse under their own gravity, igniting the birth of new stars. But it doesn't stop there. The same process also creates the building blocks for planets, as leftover material from star formation clumps together to form protoplanetary disks. Over time, these disks can give rise to entire planetary systems. What's truly remarkable is how efficient this recycling process is. The gas and dust that once belonged to older stars, now long gone, are being repurposed to create new celestial bodies. This means that the elements essential for life, like carbon, oxygen, and nitrogen, are being redistributed throughout the galaxies. In a way, the Antennae Galaxies are not just colliding, they're also giving birth to new possibilities, ensuring that the cycle of creation continues. This cosmic recycling isn't just a one-time event. As the galaxies continue to merge, the process will repeat itself, with gas and dust being cycled through multiple generations of stars and planets. It's a testament to the dynamic nature of the universe, where destruction and creation are two sides of the same coin. By studying this phenomenon, astronomers gain a deeper understanding of how galaxies evolve and how the building blocks of life are spread across the cosmos. As we marvel at this intricate dance of destruction and renewal, we're reminded that the universe is a place of endless transformation. And with that, we turn our attention to another intriguing force shaping the Antennae Galaxies, the role of magnetic fields in their evolution. Now, let's shift our focus to another invisible yet powerful force shaping the Antennae Galaxies' magnetic fields. While we often think of gravity as the dominant force in galactic collisions, magnetic fields play a crucial role in influencing how these galaxies evolve and interact. These fields, though invisible to the naked eye, weave through the fabric of the galaxies, shaping the movement of gas, dust, and even the formation of stars. During the collision, the magnetic fields within the Antennae Galaxies become highly dynamic. As the galaxies merge, their magnetic fields twist, stretch, and amplify, creating a complex web of forces that guide the flow of material. This magnetic turbulence can channel gas and dust into specific regions, accelerating the formation of dense molecular clouds where new stars are born. In a way, magnetic fields act like cosmic architects, directing the chaos of the collision into pockets of creation. One of the most intriguing effects of these magnetic fields is their ability to influence the alignment of dust particles. As gas and dust swirl through the galaxies, magnetic forces can cause these particles to align in specific directions, creating patterns that astronomers can observe. This alignment not only affects how light travels through the galaxies, but also provides clues about the strength and orientation of the magnetic fields themselves. By studying these patterns, scientists can piece together a clearer picture of how magnetic fields shape the galaxy's structure. Magnetic fields also play a role in regulating the flow of cosmic winds' powerful streams of charged particles ejected by supernovae and black holes. These winds, driven by magnetic forces, can sweep through the galaxies, redistributing gas and dust and influencing where new stars form. In some cases, magnetic fields can even suppress star formation by preventing gas from collapsing into dense clouds. This delicate balance between creation and suppression highlights the intricate interplay between magnetic fields and the galaxy's evolution. What's truly fascinating is how these magnetic fields are not static. They evolve alongside the galaxies, responding to the chaotic forces of the collision. As the Antennae Galaxies continue to merge, their magnetic fields will continue to shape their destiny, influencing everything from star formation to the distribution of cosmic material. By understanding the role of magnetic fields, astronomers gain deeper insights into the complex processes that drive galactic evolution. As we explore the invisible forces at work in the Antennae Galaxies, we're reminded that the universe is full of hidden mechanisms shaping its grand design. And with that, we turn our attention to another mystery: the challenge of measuring the exact distance to these colliding galaxies and why it matters for understanding their phenomena. Now, let's venture into a challenge that has puzzled astronomers for decades, determining the exact distance to the Antennae Galaxies. While these colliding galaxies are a stunning sight in the night sky, pinning down how far away they truly are is no simple task. Measuring cosmic distances is one of the most fundamental yet complex aspects of astronomy, and the Antennae Galaxies are no exception. Understanding their distance is crucial because it directly impacts how we interpret their size, brightness, and the scale of the phenomena unfolding within them. One of the primary methods astronomers use to measure distances to galaxies is by observing certain types of stars, known as standard candles, whose intrinsic brightness is well understood. By comparing how bright these stars appear from Earth to their known brightness, scientists can calculate the distance. However, in the case of the Antennae Galaxies, this method becomes tricky. The intense star formation and chaotic environment caused by the collision make it difficult to isolate and study individual stars with precision. Dust and gas clouds further obscure our view, adding another layer of complexity. Another approach involves using redshift, the stretching of light as galaxies move away from us due to the expansion of the universe. By measuring how much the light from the Antennae Galaxies has shifted toward the red end of the spectrum, astronomers can estimate their distance. But even this method has its limitations. The Antennae Galaxies are relatively close in cosmic terms, and their motion isn't solely influenced by the universe's expansion. Local gravitational interactions, such as those with nearby galaxies, can skew the results, making it harder to get an accurate measurement. Why does this distance matter so much? For one, it helps us understand the true scale of the phenomena we're observing. If we underestimate the distance, we might overestimate the size and brightness of the galaxies, leading to incorrect conclusions about their structure and activity. Conversely, overestimating the distance could make the galaxies appear smaller and dimmer than they really are. Accurate distance measurements also allow us to calculate the energy output of events like supernova and gamma-ray bursts, giving us a clearer picture of the forces at play in these colliding galaxies. Moreover, knowing the distance to the Antennae Galaxies helps astronomers place them within the larger context of the universe. It allows us to map their position relative to other galaxies and understand their role in the cosmic web. This, in turn, provides insights into how galaxies evolve and interact over time, shedding light on the broader processes that shape the universe. As we grapple with the challenges of measuring the Antennae Galaxies' distance, we're reminded of the intricate dance between observation and interpretation in astronomy. Every measurement, no matter how precise, carries with it a margin of uncertainty, pushing scientists to refine their methods and tools. And with that, we turn our gaze to another fascinating aspect of these galaxies, the frequent supernova explosions that light up their skies and reshape their future. Now, let's shift our focus to one of the most dramatic and transformative events in the cosmos, supernova. In the Antennae Galaxies, these colossal explosions are not just rare spectacles. They are frequent and powerful forces that shape the very fabric of these colliding galaxies. Supernova occur when massive stars reach the end of their life cycles, exploding with such intensity that they can outshine entire galaxies for a brief moment. In the Antennae Galaxies, the collision has created the perfect conditions for these stellar fireworks, making them a hotspot for supernova activity. The collision between the two galaxies has triggered an extraordinary burst of star formation, leading to the birth of many massive stars. These stars, much larger and hotter than our Sun, burn through their fuel quickly, living fast and dying young. When they exhaust their nuclear fuel, their cores collapse, resulting in a supernova explosion. These explosions release an immense amount of energy, ejecting heavy elements like iron, gold, and uranium into space. This process, known as nucleosynthesis, enriches the surrounding gas and dust, providing the raw materials for future generations of stars and planets. But the impact of supernova goes far beyond just creating new elements. These explosions also generate powerful shock waves that ripple through the interstellar medium, compressing gas and dust clouds and triggering the formation of new stars. In this way, supernova act as cosmic recyclers, turning the remnants of dead stars into the building blocks of new ones. In the Antennae Galaxies, this cycle is happening on an accelerated scale, thanks to the collision-driven star formation. Supernova also play a crucial role in shaping the galaxy's structure. The energy released by these explosions can heat the surrounding gas, preventing it from collapsing to form new stars. This feedback mechanism helps regulate the rate of star formation, ensuring that galaxies don't burn through their gas reserves too quickly. In the Antennae Galaxies, this balance is particularly delicate, as the collision has already created an environment ripe for rapid star formation. Supernova help maintain this equilibrium, preventing the galaxies from exhausting their resources too soon. Moreover, supernova are key players in the evolution of galaxies. The heavy elements they produce are essential for the formation of planets and, ultimately, life. Without supernova, the universe would lack the diversity of elements needed to create complex structures like Earth. In the Antennae Galaxies, the frequent supernova explosions are not just destructive events. They are creative forces driving the evolution of these galaxies and shaping their future. As we marvel at the power of supernova, we're reminded of the interconnectedness of cosmic processes. These explosions, born from the death of stars, give rise to new beginnings, fueling the cycle of creation and destruction that defines the universe. And with that, we turn our attention to another intriguing aspect of the Antennae Galaxies, their age, and what it reveals about the early universe. Now, let's journey back in time to uncover the age of the Antennae Galaxies and what their collision tells us about the early universe. These galaxies are estimated to be around 1.2 billion years old, a relatively young age compared to the universe itself, which is approximately 13.8 billion years old. But what makes the Antennae Galaxies so fascinating is not just their age, it's the fact that their ongoing collision offers us a rare glimpse into the chaotic processes that shape the cosmos in its infancy. When we observe the Antennae Galaxies, we're essentially looking at a snapshot of the universe's formative years. The collision between these two galaxies mirrors the kinds of interactions that were far more common in the early universe, when galaxies were closer together and collisions were frequent. By studying the Antennae Galaxies, astronomers can piece together how galaxies evolved, merged, and grew over billions of years. It's like having a time machine that allows us to witness the building blocks of the universe in action. One of the key insights we gain from the Antennae Galaxies is how star formation was likely triggered in the early universe. The collision has created an environment where gas and dust are compressed, leading to the rapid birth of new stars. This process, known as starburst activity, was much more intense in the early universe when galaxies were still forming and colliding regularly. The Antennae Galaxies give us a front-row seat to this cosmic drama, helping us understand how the first generations of stars and galaxies came to be. Another intriguing aspect of the Antennae Galaxies' age is the role of heavy elements or metals in their evolution. In the early universe, the first stars were composed almost entirely of hydrogen and helium, the simplest elements. But as these stars lived and died, they forged heavier elements through nuclear fusion and supernova explosions. The Antennae Galaxies, with their frequent supernova and intense star formation, are rich in these heavy elements. This enrichment process is crucial for the formation of planets and ultimately life. By studying the Antennae Galaxies, we can trace how the universe transitioned from a simple, pristine state to the complex, metal-rich cosmos we see today. The collision also provides clues about the role of dark matter in the early universe. Dark matter, which makes up a significant portion of the universe's mass, played a key role in shaping the structure of galaxies. In the Antennae Galaxies, the gravitational effects of dark matter are evident in the way the galaxies interact and merge. Understanding how dark matter influenced the Antennae Galaxies helps us piece together how it shaped the universe's large-scale structure billions of years ago. As we reflect on the age of the Antennae Galaxies, we're reminded that these colliding giants are more than just a cosmic spectacle. They're a window into the past. By studying them, we gain invaluable insights into the processes that shaped the early universe and set the stage for the galaxies, stars, and planets we see today. And with that, we turn our attention to another fascinating aspect of these galaxies, the role of interstellar dust and how it shapes our observations of the cosmos. Now, let's shift our focus to a phenomenon that might seem subtle at first, but plays a massive role in how we perceive the Antennae Galaxies' interstellar dust. This cosmic dust, made up of tiny particles of carbon, silicon, and other elements, might appear insignificant, but it has a profound impact on our observations. Interstellar dust acts like a cosmic veil, obscuring parts of the galaxies and making it challenging to see what's happening behind it. But here's the twist: this dust isn't just an obstacle, it's also a key player in the galaxy's evolution. When we observe the Antennae Galaxies, the dust clouds scatter and absorb light, particularly in the visible spectrum. This means that some of the most dramatic events, like star formation or the activity around black holes, can be hidden from view. However, astronomers have found ways to peer through this dusty curtain by using different wavelengths of light. For example, infrared light can penetrate the dust, revealing the hidden processes taking place within the galaxies. This ability to observe in multiple wavelengths has been crucial in uncovering the secrets of the Antennae Galaxies. But interstellar dust isn't just a barrier, it's also a building block. These tiny particles are the raw materials for new stars and planets. When dust clouds collapse under gravity, they form dense regions where stars are born. In the Antennae Galaxies, the collision has stirred up these dust clouds, creating the perfect conditions for intense star formation. The dust doesn't just obscure, it also fuels the very processes that make these galaxies so dynamic and fascinating. Another intriguing aspect of interstellar dust is how it interacts with light. Dust particles can scatter shorter wavelengths of light, like blue and ultraviolet, more than longer wavelengths like red and infrared. This phenomenon, known as interstellar reddening, gives the galaxies a reddish hue when viewed in certain wavelengths. It's a subtle effect, but it provides valuable clues about the composition and distribution of dust within the galaxies. By studying these effects, astronomers can map out where the dust is concentrated and how it influences the galaxy's structure. Interstellar dust also plays a role in the galaxy's energy balance. As stars form and die, they release energy that heats up the surrounding dust, causing it to glow in infrared light. This thermal emission is a key signature of star-forming regions, and it helps astronomers identify areas where new stars are being born. In the Antennae Galaxies, the collision has created a chaotic environment where dust is constantly being heated and reshaped, making it a hotspot for infrared observations. So, while interstellar dust might seem like a nuisance at first glance, it's actually a vital component of the Antennae Galaxies story. It shapes how we see these galaxies, influences their evolution, and even provides the raw materials for new stars and planets. By studying this cosmic dust, we gain a deeper understanding of the complex processes at work in these colliding giants. And with that, we're ready to explore another fascinating aspect of the Antennae Galaxies, their metallicity and what it tells us about the history of star formation in the universe. Now, let's turn our attention to a fascinating aspect of the Antennae Galaxies that reveals much about their history and future: metallicity. Metallicity refers to the abundance of elements heavier than hydrogen and helium, such as carbon, oxygen, and iron within a galaxy. These elements, often called metals in astronomy, are crucial for understanding how stars and planets form and evolve. In the case of the Antennae Galaxies, their metallicity tells a story of cosmic recycling and the birth of new stellar generations. When we talk about metallicity, we're essentially looking at the chemical fingerprint of a galaxy. In the early universe, galaxies were composed almost entirely of hydrogen and helium, the simplest and lightest elements. Over time, as stars formed, lived, and died, they forged heavier elements in their cores and scattered them into space through supernova explosions. This process enriched the surrounding gas and dust with metals, creating the building blocks for future stars and planets. The Antennae Galaxies, being the result of a massive collision, have experienced an intense period of star formation and stellar death, leading to a higher concentration of these heavy elements. But why does metallicity matter? For one, it directly influences the types of stars that can form. Stars born in metal-rich environments, like those in the Antennae Galaxies, tend to have different properties compared to stars formed in metal-poor regions. Higher metallicity can lead to the formation of smaller, cooler stars, as the metals help cool the gas clouds, allowing them to collapse into less massive objects. On the other hand, metal-poor environments are more likely to produce massive, hot stars. This balance of elements shapes the overall character of a galaxy's stellar population. In the Antennae Galaxies, the collision has stirred up vast amounts of gas and dust, creating regions with varying levels of metallicity. Some areas, particularly those near the cores of the original galaxies, are rich in metals due to the long history of star formation and supernova. Other regions, especially in the tidal tails, may have lower metallicity, reflecting the pristine gas pulled out during the collision. This mix of metal-rich and metal-poor regions provides a unique laboratory for studying how metallicity affects star formation on a galactic scale. Metallicity also plays a critical role in the formation of planets. Elements like carbon, oxygen, and iron are essential ingredients for rocky planets and the complex molecules needed for life. In the Antennae Galaxies, the abundance of these elements suggests that any newly forming planetary systems could have the raw materials necessary for Earth-like worlds. This makes the galaxies not only a site of intense star formation, but also a potential cradle for future planetary systems. By studying the metallicity of the Antennae Galaxies, astronomers can piece together the history of star formation and chemical enrichment over billions of years. It's like reading a cosmic diary where each element tells a story of stellar birth, death, and rebirth. And as we continue to explore these colliding giants, we gain deeper insights into how galaxies evolve and how the universe itself grows richer with time. With that, let's move on to another intriguing phenomenon: gravitational waves and their potential role in the Antennae Galaxies' cosmic dance. Now, let's shift our gaze to a phenomenon that ripples through the very fabric of space and time: gravitational waves. These elusive waves, predicted by Einstein's theory of general relativity, are disturbances in space-time caused by massive objects accelerating, such as merging black holes or neutron stars. In the case of the Antennae Galaxies, the ongoing collision and eventual merger of their supermassive black holes could produce some of the most powerful gravitational waves in the universe. Gravitational waves are like cosmic echoes, carrying information about the events that created them. When two supermassive black holes spiral toward each other, they warp space-time, sending out ripples that travel across the cosmos at the speed of light. The Antennae Galaxies, with their two black holes destined to collide, offer a unique opportunity to study these waves and the extreme physics behind them. While we haven't yet detected gravitational waves from this specific system, the possibility is tantalizing for astronomers. The merger of supermassive black holes is a cataclysmic event, releasing an enormous amount of energy in the form of gravitational waves. These waves could provide insights into the masses, spins, and orbits of the black holes, as well as the dynamics of their collision. For the Antennae Galaxies, this merger is still millions, if not billions, of years away, but it's a process that could one day be observed with advanced detectors like the Laser Interferometer Space Antenna, or LISA, a planned space-based observatory designed to hunt for low-frequency gravitational waves. Detecting gravitational waves from the Antennae Galaxies would not only confirm the presence of merging black holes, but also help us understand how such systems evolve over time. It could shed light on how galaxies grow and merge, as well as the role black holes play in shaping their environments. Moreover, these waves could reveal new details about the nature of spacetime itself, testing the limits of our current theories of gravity. While the detection of gravitational waves from the Antennae Galaxies remains a future possibility, the very idea underscores the importance of this cosmic collision. It's a reminder that the universe is not just a static backdrop, but a dynamic, ever-changing stage where even the most massive objects are in constant motion. As we continue to explore the Antennae Galaxies, we inch closer to unlocking the secrets of these invisible ripples and the profound stories they tell about the cosmos. With that, let's turn our attention to another striking feature of these galaxies: their extraordinary luminosity and what it reveals about their activity. Now, let's illuminate another fascinating aspect of the Antennae Galaxies: their extraordinary luminosity. These colliding galaxies shine with an intensity that captures the attention of astronomers across the electromagnetic spectrum, but it's in the infrared and X-ray wavelengths where their brilliance truly stands out. This extreme luminosity isn't just a cosmic light show. It's a window into the galaxy's most energetic and hidden processes. In the infrared spectrum, the Antennae Galaxies glow brightly due to the vast amounts of dust heated by newborn stars. This dust, often invisible in optical light, absorbs the energy from these young stars and re-emits it as infrared radiation. The result is a galaxy that appears to blaze with warmth, revealing regions of intense star formation that would otherwise remain hidden. This infrared glow tells us that the collision isn't just a destructive event, it's also a creative one, fueling the birth of countless stars. But the story doesn't end there. When we shift our gaze to X-ray wavelengths, the Antennae Galaxies reveal another layer of their activity. Here, the galaxies are teeming with X-ray sources, including black holes, neutron stars, and hot gas clouds. These X-rays are produced by some of the most extreme environments in the universe, where matter is heated to millions of degrees and particles are accelerated to near light speeds. The presence of so many X-ray sources underscores the chaotic and energetic nature of the collision, as well as the galaxy's role as cosmic laboratories for high-energy physics. What's particularly striking is how these two forms of luminosity, infrared and X-ray, complement each other. The infrared light shows us the birth of stars, while the X-rays reveal the aftermath of stellar explosions and the activity of black holes. Together, they paint a vivid picture of a galaxy in flux, where creation and destruction are intertwined on a cosmic scale. This extreme luminosity also has broader implications for our understanding of galactic evolution. By studying the Antennae Galaxies, astronomers can learn how collisions trigger star formation, how black holes grow and interact, and how galaxies transform over time. It's a reminder that light, in all its forms, carries the stories of the universe, stories that we are only beginning to decode. As we marvel at the Antennae Galaxies' brilliance, let's turn our attention to another force shaping their destiny, the powerful cosmic winds that sweep through their interstellar medium, sculpting their structure and influencing their future. Now, let's shift our focus to the invisible yet mighty forces at work within the Antennae Galaxies' cosmic winds. These powerful streams of gas and particles, driven by the explosive energy of supernovae and the intense gravitational pull of black holes, play a crucial role in shaping the galaxy's structure and evolution. Imagine these winds as cosmic sculptors, carving out vast regions of space and influencing the birth and death of stars. Cosmic winds originate from some of the most energetic events in the universe. When massive stars end their lives in supernova explosions, they release enormous amounts of energy, propelling gas and dust outward at incredible speeds. Similarly, the supermassive black holes at the centers of galaxies can generate winds as they consume matter, heating it to extreme temperatures and ejecting it into space. In the Antennae Galaxies, these winds are particularly intense due to the ongoing collision, which amplifies the activity of both supernova and black holes. These winds don't just blow aimlessly, they have a profound impact on the galaxy's structure. As they sweep through the interstellar medium, they can compress gas clouds, triggering the formation of new stars. At the same time, they can also strip away material from existing stars and star-forming regions, effectively halting star formation in some areas. This dual role makes cosmic winds a key player in the delicate balance between creation and destruction within the galaxies. But the influence of cosmic winds extends beyond star formation. They also help regulate the galaxy's chemical composition by dispersing heavy elements forged in the hearts of stars and supernova throughout the interstellar medium. This process, known as galactic recycling, ensures that future generations of stars and planets have the raw materials they need to form. In this way, cosmic winds are not just destructive forces, they are also essential agents of renewal and transformation. The study of cosmic winds in the Antennae Galaxies offers valuable insights into how galaxies evolve over time. By observing how these winds interact with their surroundings, astronomers can better understand the mechanisms that drive galactic change, from the smallest scales of star formation to the largest scales of galactic structure. It's a reminder that even the most chaotic processes in the universe are governed by underlying patterns and principles. As we explore the role of cosmic winds, we're reminded of the dynamic and interconnected nature of the Antennae Galaxies. These winds are just one piece of the puzzle, but they highlight the intricate dance of forces that shape the cosmos. Next, we'll delve into how the Antennae Galaxies serve as a window into the broader processes of galactic evolution, offering clues to the mysteries of the universe itself. Now, let's turn our attention to a question that has fascinated astronomers for decades. What can the Antennae Galaxies teach us about the broader story of galactic evolution? These colliding galaxies are more than just a stunning cosmic spectacle. They're a living laboratory, offering scientists a front-row seat to the processes that shape galaxies across the universe. By studying the Antennae Galaxies, researchers can piece together the intricate puzzle of how galaxies grow, change, and interact over billions of years. One of the most significant insights from the Antennae Galaxies is how galactic collisions drive evolution. When two galaxies collide, the resulting chaos triggers a cascade of events: intense star formation, the activation of supermassive black holes, and the redistribution of gas and dust. These processes, observed in real time within the antennae, mirror what scientists believe happened during the early universe, when galaxy collisions were far more common. By analyzing this collision, astronomers can better understand how galaxies in the distant past evolved into the diverse structures we see today. Another key takeaway is the role of feedback mechanisms in galactic evolution. The Antennae Galaxies showcase how phenomena like supernova, black hole activity, and cosmic winds regulate star formation and shape the galaxy's structure. These feedback loops are crucial for maintaining balance within galaxies, preventing them from either burning through their gas too quickly or becoming stagnant. Understanding these mechanisms helps scientists explain why some galaxies are bustling with star formation while others appear quiet and dormant. The Antennae Galaxies also provide a unique opportunity to study the life cycle of stars and the chemical enrichment of galaxies. As stars are born, live, and die within these colliding systems, they release heavy elements into the surrounding space. This process, known as chemical evolution, is essential for the formation of planets and potentially life. By observing the antennae, astronomers can trace how these elements are distributed and recycled, offering clues about the origins of the building blocks of life itself. Perhaps most importantly, the Antennae Galaxies remind us that galaxies are not static entities, they are dynamic, ever-changing systems. The collision we're witnessing today is just one chapter in a much larger story. Over time, the antennae will merge into a single elliptical galaxy, a process that has occurred countless times throughout the universe's history. By studying this transformation, scientists can predict the future of other galaxies, including our own Milky Way, which is on a collision course with the Andromeda Galaxy. In essence, the Antennae Galaxies serve as a cosmic time machine, allowing us to peer into the past, present, and future of galactic evolution. They reveal the interconnectedness of the universe, showing how even the most chaotic events are part of a larger, orderly process. As we continue to unravel their secrets, we gain not only a deeper understanding of the antennae themselves, but also a clearer picture of how galaxies, including our own, came to be. Next, we'll explore the Antennae Galaxies' place in the cosmic web and their significance in our quest to understand the universe as a whole. Now, let's take a step back and consider the Antennae Galaxies not just as a pair of colliding systems, but as a vital piece of the cosmic puzzle. These galaxies are more than a spectacle. They are a window into the intricate web of connections that bind the universe together. the Antennae Galaxies remind us that no galaxy exists in isolation. They are part of a vast network known as the cosmic web, a structure made up of galaxies, gas, and dark matter that stretches across the universe. This web is the backbone of cosmic evolution, and the antennae are a vivid example of how galaxies interact within this grand framework. One of the most profound lessons the Antennae Galaxies teach us is about the interconnectedness of the universe. Their collision is not just a local event, it's a reflection of the forces that shape the cosmos on the largest scales. The gravitational interactions that created their iconic tidal tails and triggered bursts of star formation are the same forces that govern the movement of galaxies within the cosmic web. By studying the antennae, scientists gain insights into how galaxies are drawn together by gravity, forming clusters and superclusters that define the structure of the universe. The Antennae Galaxies also highlight the role of feedback in shaping the cosmic web. The energy released by supernova, black holes, and cosmic winds doesn't just affect the galaxies themselves. It ripples out into the surrounding space, influencing the distribution of gas and the formation of new galaxies. This feedback is a key driver of the cosmic web's evolution, and the antennae provide a close-up view of how these processes work. Understanding this helps astronomers piece together how the universe has grown and changed over billions of years. Moreover, the Antennae Galaxies offer a glimpse into the future of our own cosmic neighborhood. As we've discussed, the Milky Way is on a collision course with the Andromeda Galaxy, and the antennae give us a preview of what that might look like. By observing their merger, we can better predict how such events shape galaxies and their surroundings. This knowledge not only deepens our understanding of the universe, but also helps us appreciate our place within it. In the grand scheme of things, the Antennae Galaxies are a reminder of the universe's dynamic nature. They show us that change is a constant, driven by the interplay of gravity, energy, and matter. As we continue to study them, we uncover not just the secrets of these two galaxies, but the broader story of how the universe evolves. The antennae are a testament to the beauty and complexity of the cosmos, and they inspire us to keep exploring, keep questioning, and keep marveling at the wonders that lie beyond our own galaxy. Now, let's zoom in closer to the heart of the Antennae Galaxies and explore the mechanics of their collision in greater detail. This cosmic event isn't just a random crash, it's a carefully orchestrated dance of gravity, matter, and energy that has been unfolding for hundreds of millions of years. To truly grasp what's happening, we need to understand the forces driving this galactic merger and the timeline that has shaped its evolution. At the core of this collision is gravity, the invisible force that binds the universe together. When two galaxies like the antennae come close enough, their mutual gravitational pull begins to warp their shapes. Imagine two massive clouds of stars, gas, and dust slowly spiraling toward each other, drawn together by an irresistible force. As they approach, their outer regions start to stretch and distort, creating the iconic tidal tails we see today. These tails are like cosmic fingerprints, marking the gravitational tug of war between the two galaxies. But gravity isn't the only player in this cosmic drama. As the galaxies collide, their gas clouds slam into each other, compressing and heating up. This triggers a burst of star formation, lighting up the galaxies with newborn stars. The densest regions of gas collapse under their own gravity, forming superstar clusters that shine brighter than anything else in the galaxies. This intense star birth is a hallmark of galactic collisions, and the antennae are no exception. The timeline of this collision is equally fascinating. Scientists estimate that the two galaxies first began interacting around 600 million years ago. At that time, they were likely separate spiral galaxies, much like our Milky Way. As they drew closer, their gravitational forces started to pull them into a slow, cosmic embrace. Around 300 million years ago, the galaxies passed through each other for the first time, creating the dramatic tidal tails we see today. This initial pass-through was just the beginning. Since then, the galaxies have continued to orbit each other, gradually merging into a single, chaotic system. What's truly remarkable is that this collision is far from over. The Antennae Galaxies are still in the process of merging, and it will take hundreds of millions more years for them to fully combine into a single elliptical galaxy. During this time, the forces at play will continue to reshape the galaxies, triggering more star formation, feeding their supermassive black holes, and recycling gas and dust into new generations of stars and planets. By studying the Antennae Galaxies, we're not just witnessing a single event, we're observing a process that has shaped the universe since its earliest days. Galactic collisions like this one are a fundamental part of how galaxies grow and evolve, and the antennae provide a front-row seat to this cosmic spectacle. As we continue to unravel the details of their collision, we gain a deeper understanding of the forces that have shaped the universe we see today. Now, let's turn our gaze to the future and explore how the ongoing collision of the Antennae Galaxies will continue to shape star formation over the next billions of years. This isn't just a fleeting cosmic event. It's a process that will leave a lasting imprint on the galaxies, influencing their evolution long after the merger is complete. As the galaxies continue to spiral closer together, the intense gravitational forces will keep compressing their gas clouds, creating the perfect conditions for new stars to ignite. This means the starburst activity we see today is just the beginning. Over the next few 100 million years, the rate of star formation is expected to peak, lighting up the galaxies with even more brilliant clusters of young stars. These newborn stars will not only add to the galaxy's luminosity, but also contribute to their chemical makeup, enriching the interstellar medium with heavier elements forged in their cores. However, as time goes on, the story of star formation in the Antennae Galaxies will take a dramatic turn. Once the galaxies fully merge into a single elliptical galaxy, the gas and dust needed to form new stars will begin to deplete. The intense bursts of star formation we're witnessing now will gradually slow down, and the galaxies will enter a quieter phase. Without a steady supply of fresh gas, the formation of new stars will become increasingly rare, and the galaxies will transition into a phase dominated by older, redder stars. But even as star formation slows, the legacy of this collision will endure. The superstar clusters born during the merger will continue to evolve, some potentially surviving as globular clusters for billions of years. These clusters will serve as cosmic time capsules, preserving the history of the Antennae Galaxies' dramatic collision for future generations of astronomers to study. What's truly fascinating is how this process mirrors the life cycle of galaxies across the universe. The Antennae Galaxies offer us a glimpse into the future of other colliding galaxies, including what might happen when our own Milky Way eventually merges with the Andromeda Galaxy. By studying the antennae, we're not just learning about their fate, we're uncovering the broader story of how galaxies grow, change, and evolve over cosmic time. As we look ahead, it's clear that the Antennae Galaxies will remain a cosmic laboratory for understanding the forces that shape the universe. Their collision is a reminder that even in the vastness of space, change is constant, and the future holds endless possibilities for discovery. Now, let's shift our focus to the incredible role technology has played in uncovering the mysteries of the Antennae Galaxies. Without the advancements in telescopes and space observatories, much of what we know about these colliding galaxies would remain hidden in the vastness of space. It's through the lens of cutting-edge technology that we've been able to peer deeper into their chaotic beauty and unravel their secrets. One of the most significant breakthroughs came with the launch of space-based observatories like the Hubble Space Telescope. Hubble's sharp vision allowed astronomers to capture stunning images of the Antennae Galaxies in unprecedented detail, revealing the intricate structures of their tidal tails, superstar clusters, and regions of intense star formation. These images not only captivated the public but also provided scientists with critical data to study the dynamics of galactic collisions. But Hubble was just the beginning. Infrared telescopes like the Spitzer Space Telescope have given us a new perspective on the Antennae Galaxies. Infrared light penetrates the thick clouds of dust that obscure visible light, allowing us to see the hidden processes at work. Through Spitzer, we've discovered that the Antennae Galaxies are even more active than they appear, with vast regions of star formation hidden behind their dusty veils. Then there's the Chandra X-ray Observatory, which has revealed the high-energy phenomena occurring within the galaxies. Chandra's observations have uncovered countless X-ray sources, including black holes, neutron stars, and hot gas clouds, painting a picture of a dynamic and violent environment. These findings have deepened our understanding of how galactic collisions influence the behavior of black holes and the distribution of matter in the universe. Ground-based telescopes have also played a crucial role. Instruments like the Atacama Large Millimeter Array, or ALMA, have allowed astronomers to study the cold molecular gas that fuels star formation. ALMA observations have shown how the collision has compressed these gas clouds, triggering the birth of new stars and superstar clusters. Looking to the future, next-generation telescopes like the James Webb Space Telescope promise to take our understanding even further. With its ability to observe in infrared wavelengths, Webb will peer deeper into the Antennae Galaxies, uncovering the earliest stages of star formation and shedding light on the chemical composition of their interstellar medium. It's through these technological marvels that we've been able to piece together the story of the Antennae Galaxies. Each new instrument brings us closer to understanding the forces that shape the universe, reminding us that the tools we build are just as important as the questions we ask. As technology continues to evolve, so too will our ability to explore the cosmos and uncover its many wonders. As we wrap up our journey through the Antennae Galaxies, it's clear that these colliding giants are more than just a cosmic spectacle. They're a treasure trove of mysteries waiting to be unraveled. From the dramatic tidal tales stretching across space to the supermassive black holes lurking in their cores, each phenomenon we've explored reveals a piece of the puzzle that is our universe. The intense star formation, the hypervelocity stars racing through the void, and the hidden infrared and X-ray emissions all paint a picture of a dynamic, ever-changing cosmos. The Antennae Galaxies remind us that the universe is a place of constant transformation, where even the most violent events can give birth to new stars, planets, and possibilities. They challenge us to think beyond our own world and consider the vast, interconnected web of galaxies that make up the cosmic tapestry. But perhaps the most fascinating aspect of the Antennae Galaxies is what they teach us about our place in the universe. By studying these colliding galaxies, astronomers gain insights into the processes that shape galaxies, the role of dark matter, and the future of our own Milky Way. They remind us that the universe is not static. It's alive with motion, energy, and mystery. As we conclude, I invite you to reflect on the wonders we've explored together. The Antennae Galaxies are just one example of the countless marvels waiting to be discovered in the cosmos. Each new observation, each technological breakthrough, brings us closer to understanding the universe and ourselves. If you've enjoyed this journey through the Antennae Galaxies, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an exploration into the mysteries of space. Let's keep uncovering the secrets of the universe together. Until next time, keep looking up. The cosmos is full of wonders waiting to be discovered.